Hi, I'm Dr. Mrittunjoy Majumdar, postdoctoral researcher at Cambridge University. And today I'm here to share with you the story of a world so unique and different that it may not quite be intuitive, not quite what one experiences in day-to-day life, the quantum world. Let us say that we have this setup for bowling, and I roll the ball like this. I will hit the pin to the left. Let us now say that we have the very same setup, but a slightly strange thing happens. Let us say this time we roll the ball in the same way, and there is something that happens between the separated walls and the pin, and this time the pin on the right falls. Impossible, you would say. Not quite. This is one of the many things that one can do in the quantum world. This is due to the dual nature of all entities. All things are both a particle and a wave. And this experiment builds on the wave-like nature of bodies. This is one of the many problems that scientists faced in the early 20th century.
We know that light helps us see all the objects around us. We also know that it can originate from sources like the sun, an electric bulb, or even a little firefly. But what is light? Is it made up of waves? Or is it made up of tiny particles like atoms? The journey of finding answers to these questions led researchers to the foundation of a revolutionary field of modern physics, the quantum mechanics. Our story begins in the 17th century when Isaac Newton gave the corpuscle model of light. Newton said that light is made up of very tiny particles called corpuscles, which are emitted when any source of light is switched on. Using this theory, he was able to explain the phenomena people knew of in those times, like reflection and bending of light in water. Around the same time, a Dutch physicist, Christian Huygens, had another story to tell. He said that light is made up of waves, which are disturbances that travel in a medium much like a sound wave. Even his theory was able to explain the phenomena of reflection and bending of light. Hence, this made the nature of light a debatable question. Is light made up of particles or waves? However, since Newton had a high reputation in those times, his particle model was a popular choice. In 1801, Newton was challenged again. An experiment by a British polymath, Thomas Young, brought the wave theory to the forefront. Young's experiment was something like this. He took a monochromatic source of light, that is, light of a single color, and made it pass through two vertical narrow slits cut in an opaque plate. The light from the slits was collected on a screen, and what he observed changed the game totally. If we take Newton's particle model of light, we would think that light from the two slits will travel in a straight line and mark two bright spots on the screen, right? But this is not what happened. The screen showed an alternating pattern of dark and bright bands. How was this possible? Newton's particle model failed to explain so. Young could, however, explain this using the wave model. A wave is a disturbance moving through a medium. The wave theory says that when two waves interact with each other, they interfere to produce a combined effect. The two waves superimpose on each other. That is, the net displacement at any point is the sum of the individual wave displacement. Thus, when light waves pass from the two slits, they reach the screen after interacting with each other in their paths. Depending on how they interact, they add up or cancel each other out, and we see alternating bright and dark bands. We had an experiment which could only be explained by the Huygens wave theory. Later on, many other experiments backed up the wave nature of light. Fresnel and Fraunhofer demonstrated the phenomenon of diffraction of light that could only be explained with the wave model. In 1860, James Clerk Maxwell went on to show that light is an electromagnetic wave with a speed of 3 × 10 to the power 8 meter per second in vacuum. Thus, in the 19th century, wave model of light was gaining control in the field of physics. But it was soon to be challenged again.
In 1900, Max Planck changed the way we saw nature. All bodies absorb and emit electromagnetic radiation. A black body is a body that absorbs all incident electromagnetic radiation, which are waves of the electromagnetic field, the physical field produced by moving electrical charged objects, regardless of frequency or angle of incidence. True black bodies, however, do not exist. The sun and the stars come closest. A close enough approximation is a black shell, with a single cavity from which light can enter, since light cannot escape easily from it, and the shell tends to absorb light of all frequencies. Black body radiation is a kind of radiation within or surrounding a body that is not emitting or receiving any heat or matter from its environment, emitted by a black body. The energy carried by light of different frequencies depends on the temperature of the black body in what is known as the black body radiation curve, which looks at the energy of various frequencies associated with the body. In the way we understood physics before quantum physics came, it was seen that the black body can release an arbitrarily high amount of energy. The theory even predicted that all bodies would emit most of their energy in the ultraviolet range, clearly contradicted by the experimental data which showed a different peak wavelength at different temperatures. In practice, this is not the case. Max Planck, however, resolved this by postulating that light tends to move in packets of energy, or quanta. He found a law that fit the experimental data well. This was the first time when classical physics was not only challenged, but displaced by a new kind of physics. Next up was a year of miracles, Annus Mirabilis, 1905, when Einstein published 4 famous papers. The explanation that gave him the Nobel Prize, however, was that of the photoelectric effect. Heinrich Hertz had discovered the effect in 1887.
Photoelectric effect was another experiment that opened the debate of whether light is a wave or a particle. In this experiment, it was seen that electrons are emitted from a metal surface when light falls on it. These electrons are called photoelectrons. Wave theory could easily explain why photoelectrons were getting emitted. Waves carry a certain amount of energy with them. When a light wave falls on a metal surface, the metal absorbs this energy and transfers it to its electrons. When an electron gets enough energy to resist the attraction from the rest of the metal, it becomes free and comes out. While this was simple to understand, scientists could not explain certain other observations using wave model. In their experiments, 2 scientists, Leonard and Millikan, observed that as soon as light falls on the metal surface, electrons are ejected almost instantaneously. This remains the same whether the source of light is strong or weak. Now, according to the wave theory, if we use a weak source of light, the electron will need some amount of time to acquire sufficient energy to break free and come out. Instantaneous emission should not be possible in that case. Next, the wave model suggests that light of any frequency should be able to eject electrons. If the source is strong and the light falls on the surface for a sufficiently long time, it should be able to transfer its energy to the electron and the electron should come out. However, experiments showed that if frequency of light is less than a certain value, called the threshold frequency, electrons are not emitted, no matter how intense the light is or how long you shine it. There was one more piece to this puzzle. According to the wave theory, energy carried by light waves is measured by the intensity of the beam. If the intensity is increased, the energy of the photoelectron must also increase. Experiments, however, showed that the maximum kinetic energy of these photoelectrons is independent of the intensity of light. Clearly, wave theory was failing to explain all these observations. And this is when Einstein came to the rescue. Einstein used quantum theory to explain the photoelectric effect. This theory says that light is made up of discrete packets or quanta of energy called photons. Each photon has a particular amount of energy associated with it. As a photon or energy packet of light falls on an electron, the electron will absorb all the energy in one go and will come out. This explains the almost instantaneous emission of photoelectrons. Now, according to the quantum theory, the energy of these light bundles or photons depends on the frequency of light and not on its intensity as in classical mechanics. Higher the frequency, more is the energy of the photon. Now, to free the electron from the metal, a minimum amount of energy or minimum frequency of light is required. Hence, if light with photons of frequency less than the threshold frequency is shown on the metal surface, the energy is not enough to break the electrons free. If the intensity of light is increased, it will increase the number of photons falling on the surface, but the energy of each photon remains the same. So increasing the intensity will not emit any photoelectron. Once we increase the frequency of the photons beyond the threshold value, the energy increases and photoelectric effect can be observed. Thus, quantum theory was successful in explaining all the observations.
When a light hits a material under certain conditions above a certain frequency, the material tends to eject electrons. According to the classical theory, the photoelectric effect can be attributed to the transfer of energy from light to the electron. From this perspective, an alteration in the intensity of light would induce changes in energy carried by the electrons emitted from the material. However, experiments showed that electrons were emitted only by the striking of photons on the material when those photons reached or exceeded certain energies. Below that threshold, no electrons were emitted from the material regardless of the light intensity or the length of time of exposure of the light. Borrowing from Planck, Einstein explained this in terms of packets of energy. Einstein's work predicted that the energy of individual ejected electrons increases linearly with the frequency or energy of the light and is independent of the intensity of light. Robert Andrews Millikan showed experimentally that this was indeed true. Experimentally, there were certain other phenomena like Zeeman, Compton, and Raman effect which would not be explained by physics till then. It's now time for a short break. We will come back to you with more about the quantum world.
India Science is an internet-based science TV channel initiated by the Department of Science and Technology, Government of India, implemented and managed by Vigyan Prasar. India Science on the URL www.indiascience.in is a bilingual channel with content in Hindi and English. It can be accessed on any internet-enabled device. This video platform is dedicated to science and technology knowledge dissemination with a strong commitment to spreading scientific awareness, especially with Indian perspectives, ethos and cultural context. The India Science mobile app can be downloaded from the Google Play Store and Apple Store.
Welcome back. Before the break, we were talking about the experimental discoveries of Zeeman, Compton, and Raman effect. At around the same time, Ernest Rutherford experimentally discovered the nuclear model of the atom, for which Niels Bohr developed his theory of the atomic structure, which was later confirmed by the experiments of Henry Moseley.
Rutherford's model says that all the mass of an atom except that of the electrons and all the positive charge is concentrated in a very small space at the center of an atom called the nucleus. The rest of the atom is a hollow sphere in which electrons move around the nucleus in circular orbits like planets move around the sun. Rutherford did propose quite a good model of an atom, but there was still something which was not making sense. According to classical mechanics and electrodynamics, any charged particle, in this case the electron, should radiate out energy when in an accelerated motion. As the electron loses energy, it shall slow down and the radius of the orbit should decrease. Thus, the electron will spiral down towards the nucleus and the atom will not be stable. To solve this problem, Niels Bohr came up with an improved model of an atom. He realized that it will be difficult to explain the stability of an atom using classical mechanics. Bohr chose the path of quantum theory. He said that the potential energy of electrons is quantized. That is, the electrons can revolve only in discrete orbits of fixed energy levels and fixed distances from the nucleus. They cannot be present anywhere between these defined orbits. While revolving in these orbits, electrons do not radiate any energy and remain stable. The electrons can, however, jump from one energy level to another by absorbing or emitting fixed amounts or quanta of energy. When the atom receives energy from outside, one or more electron can absorb this energy and move to a higher orbit. This is called the excited state of an atom. Similarly, the electron can lose energy in the form of electromagnetic waves and move to a lower orbit. In the history of atomic science, Bohr's model was a great achievement.
The classical theory was clear. An electron orbiting the nucleus would be accelerating and radiating energy. In the process, it will lose energy and fall deeper into the attractive pull of the nucleus and eventually crash into the nucleus. Niels Bohr introduced a radical idea. He posited that there are stable orbits arrayed around the nucleus in which the electron could orbit indefinitely without losing any energy. If not in these orbits, the instability reappeared. The energy of the electrons in the various orbits are separated by discrete packets of energy. The foundations of quantum mechanics were established during the first half of the 20th century by Max Planck, Niels Bohr, Werner Heisenberg, Louis de Broglie, Arthur Compton, Albert Einstein, Erwin Schrödinger, Max Born, John von Neumann, Paul Dirac, Enrico Fermi, Wolfgang Pauli, Satyendranath Bose, and Arnold Sommerfeld. This is the picture of the famous Solvay Conference in 1927, where a number of these greats came together for the first time. Continuing from Planck and Einstein's work on light as a set of packets of energy, the question was, is light a particle or is it a wave? If this corpuscular view of light is so successful, do we need the wave view at all? In 1909, Einstein showed that certain phenomena could only successfully be explained if we used both the wave and the particle view, in what was called the wave-particle duality. Since while the particle picture of light explained black-body radiation and the photoelectric effect, phenomena like Young's interferometry required the wave nature of light. De Broglie, in his 1924 PhD thesis, proposed that just as light has both wave-like and particle-like properties, electrons also have wave-like properties. So any particle or light photon could have both a wave-like and a particle-like tendency at the same time. As per de Broglie's work, it was first mathematically and then experimentally shown that faster the particle, smaller is the wavelength of the associated wave. And slower the particle, longer is the wavelength. Remember the Bohr model of the atom that spoke of stable orbits of electrons? While it was good for one-electron systems, for multi-electron systems it had its problems. The Bohr model could explain the properties of the energy released by such systems when electrons transitioned. Heisenberg objected to this model because he claimed that since one couldn't actually observe the orbit of an electron around a nucleus, such orbits couldn't really be said to exist. One could only observe the spectrum of light emitted or absorbed by such atoms. Starting in 1925, Heisenberg set to work trying to come up with a quantum mechanics that relied only on properties that could, at least in theory, be observed. Heisenberg developed a new approach to quantum mechanics. He took quantities such as position and velocity and found a new way to represent and manipulate them mathematically. This way of treating phenomena led him naturally to the famous uncertainty principle. In the classical world, we can measure properties such as position and velocity at the same time. However, in the quantum world, as per the uncertainty principle, certain pair of properties such as momentum position, energy time of a particle cannot be known to the maximum degree simultaneously. So if the position of a particle is known to a high degree of accuracy, the same will not be the case with its momentum. This was a journey that great minds took at the start of the 20th century and found phenomena so bizarre, so outlandish, that a whole new world was discovered, that of quantum physics. In fact, it was so bizarre that a new set of rules had to be made for the particles. So what are these rules? We will talk about this after a quick break.
India Science is an internet-based science TV channel initiated by the Department of Science and Technology, Government of India, implemented and managed by Vigyan Prasar. India Science on the URL www.indiascience.in is a bilingual channel with content in Hindi and English. It can be accessed on any internet-enabled device. This video platform is dedicated to science and technology knowledge dissemination with a strong commitment to spreading scientific awareness, especially with Indian perspectives, ethos and cultural context. The India Science mobile app can be downloaded from the Google Play Store and Apple Store.
Welcome back after the break. Let us consider a quantum particle. In the classical world, bodies can be attributed by their mass, their volume, their displacement, velocity, or acceleration. In the quantum world, all the properties, all the descriptions are stored in one single entity called the wave function. This wave function is a wave that is not quite physical but more mathematical and gives us an idea of the probability of finding this particle in a certain space. In the classical world, one can measure properties of the particles such as length, mass, volume, and displacement. This could take any value on the scales. In the quantum world, the scales are rather discrete. One can only have specific values of measurements for the measurement of these properties. But that is not all. In the classical world, one can only have one value for a property. A body can have one length, a particular weight, and a definite displacement. This is not the case in the quantum world. The properties of the particle could have a number of possible values. Each value has a certain probability of happening. Let us name each probability as alpha, beta, and gamma, and so on. A particular value is only obtained upon measurement. The one place where both these worlds are similar is in the conservation of energy and how the bodies move in time. In the classical world, we have a potential energy, say of this ball at a certain height, which is the stored energy it possesses due to its position in this case, which gets converted into its kinetic energy the energy it possesses due to its motion once dropped. In the quantum world, it is similar with a distinct potential and kinetic energy. But the total energy is not just a quantity, but the probabilistic outcome of a quantum operation. Similar to the previous example, it can have a number of outcomes. In the quantum world, we have a probabilistic formalism, a world full of chances and probabilities. But when we do a measurement of any properties, there is a specific answer, a certain collapse, so to say. It is this wonderful reality that physicists are still studying till date, with eminent physicists from Niels Bohr to David Bohm having given different interpretations about the foundations of quantum mechanics. Having looked at the wonderful and strange world of quantum mechanics, let us now look at one application of quantum mechanics, that being of quantum computation. All computers, including supercomputers, have the problem of them running out of storage. We know that computers have bits, 0 and 1, usually. We can make binary sequences with them. But what if I were to give you not just two valued bits, but an infinite valued quantum bit? Instead of 0 and 1, let us have a quantum particle that has probability alpha for it to be 0 and probability beta for it to be 1. And these probabilities can vary depending on the operations. Since the basic building block itself increases from two valued to multiple valued, the computing power increases immensely. Also, since size matters, we have come a long way from the days of UNIVAC to personal computers, and now with quantum computers, we may be able to have a supercomputer on our palms. This brings us to the end of our journey in the world of quantum physics, a world that is beyond what we experience in day-to-day life. Thank you and goodbye.